Great. So we are here to discuss two topics related to text processing and text search, text indexing. What we will start with, the things around the classical approach to how to search fastly for a text, yeah, and how it was done 50 years ago, 20 years ago, and even 5 years ago. Because this approach, the inverted index, is very powerful. Maybe you already know this technique, maybe not, but I think that there will be knowledge which is also important, like some specific things. So what we speak about, first we'll start with languages, the formal statement of what is language and how we use this knowledge about languages in our indexing. And then we'll speak about building an inverted index in the first lecture. Before we start, a quick check. 4 simple questions about what was in the previous lecture. So who can say what is DNS?
It's a server which transforms URL addresses into IDs.
Not exactly. DNS, domain name service. It's a service. It's a collection of servers, not a single machine, but multiple machines. At least 13 them in the root level and some others below, which transform not URLs, but domain names. So domain name is just a part of URL. So something which goes among, between slashes. Okay. Not schema. Schema is what is the protocol of communication, and domain name is what is, I don't know, telegram.org, mail.ru, innopolis.university. This is domain name, and this service allows both direction translation of these names into numbers and numbers into names. Okay, HTTP. What is this? Maybe someone online. No one remembers. Okay.
Hypertext transfer protocol. It's
okay.
a protocol to send documents across the world.
Protocol to send documents. From the name, it's obvious. It's the protocol to transfer hypertext, or hypertext is just an extension of text. So some text information which allows you to link one document to another. In today's understanding, you can call hypertext whatever is media. So it can be text with videos, text with images, text with links, so something which is richer than just a text. But still, we stick to the definition that this is text. Okay, text means the limited char set always. So binary information allows you to use the whole palette of bytes from 0 to 2555. Hypertext limits to whatever is text. Text is usually starting from the I don't know, from the 10th symbol. Like the first symbols are specific characters. The upper part of the ASCII table is sometimes misused. So like there's a limited char set. That's why the information which you send over internet using HTTP is usually sent with redundancy. So you want to send a gigabyte of video, it will take around 1.5 gigabytes of data to send using HTTP, because it will convert this video into text, and text requires slightly more space. HTTPS, what's the difference? Yeah, definitely.
Can I answer?
Secured, there was an answer. Yeah, so there's a secured channel built between machines using like a handshake procedure, using an asymmetric key exchange and symmetric cryptography, which allows to take this text from HTTP, encrypt it in the way that even if you use a channel which is untrusted, like the Wi-Fi in university, or just a cord, Ethernet cord, which someone can just plug into and copy the data, still it will be undecryptable, like at least at current machines. And it will be more or less safe communication between parties. Also, it has another function when we speak about certificates. The infrastructure of certificates allows you not only to protect the communication, but also verify that the other party, which you actually communicate into, is the party you want to communicate. I explained you the case with Kazakhstan, when government wanted to install the intermediate server between a human and Google. Yeah, and they wanted to filter out the traffic which you send, and they wanted to substitute the certificate. They wanted to issue their own certificate to Google. google.com, yeah, and it was the case. So if you trust the authorities which issue the certificates, you will always know whether this is actually the party you want to communicate to, or there is a man in the middle. If you see untrusted certificate, means that something went wrong. Maybe the certificate is outdated, maybe there is a man in the middle, something. Okay, and from your homeworks and contests, what's headless browser? So browser without head, yeah, browser without interface. So the software which allows you to render the website without displaying it to a screen. Yeah, it's a very useful tool to render pages in software. So it's mostly the tool for writing the code, not for using it as a personal user. Okay, languages. So any language can be described in the concept of three perspectives. Three perspectives are pragmatics, how we use the language. So for what reason we use the language. I can order pizza in C++, but this is not pragmatical because like the person on the other side cannot understand C++. The person knows English or Russian. And yeah, there's a chance to write something down, but the pragmatics is this. If I, for example, use a lots of data transformation in my language, like which are like can be explored as mappings, chainings, filtering, Python is a perfect language. If I want to do the same in C, that's not very pragmatic. The pragmatics of my language is not that cool. But we are not speaking about pragmatics because we are staying in the field of natural language, like which is mostly like English here and some other some other languages. But we stick to the idea that the natural language, is used for communicating between humans or between human and the machine right now. So this is the most common case. Machines communicate in different languages between themselves. Okay, so human with machine, human with human use language to communicate. English, Russian, and so on. Then comes semantics. Semantics means something which is very not very well defined, but it's about the meaning of sentences and words. So there's semantics which can be given to a sentence, to a word, and here you see the sentences with like the decreasing semantics, meaning that the first one is a valid sentence in English. The second one is the sentence where each word has some meaning. It's the normal word from English, but altogether the sentence is meaningless. So the words are in some wrong positions. Then there is the example of the sentence which looks like English, but none of these words actually, maybe instead of articles, they have some meaning. So they're the meaningless words in terms of our understanding of language. And the last one is just the collection of letters is the same. It's still English letters, but there are not words. They are not look like English words, and so on. So there is no even a glance of semantics in this sentence. So semantics is about meaning, and we will speak about how to model a meaning in this and the next block of lectures. And the one which is the most formally well defined is grammar, like syntax of the language, is the way how to write in this language, let's say correctly. Yeah. And again, you don't have to think that there is a single syntax well defined for language, because all these sentences are sentences in English, but they misuse grammar of English in a different way. The first one is from my childhood meme. It's about the kitten who is asking for a cheeseburger, and you see that you understand the sentence, but it's written like incorrectly in terms of English. The next one has a lot of typos, so that most of these words are never appear, like they don't ever appear in the vocabulary of English language. The third one is, again, it can be the sentence in English, but some of these words never were in the vocabulary of English 50 years ago, for example. Yeah, like the word bro or chuffed to bits, which is the phrasal verb in English. And the last one is abbreviations. And like I always want to insert example with emojis, and I always forget. So you should understand that today emoji is also a part of a language. Yeah, so it will be again the part of English, and the syntax and the grammar of language is changing rapidly today. But this is about how to write in English. We are somewhere in the place when you can read these sentences and understand. So they preserve some rules which are actually saying that this is English, and you apply your brain to decode English here. Okay, let's speak about the last one, the syntax, the most formal thing. So by definition, syntax, which is a linguistic term, so it's not a computer science term, is the thing which guards word order. So how to put letters in words and words in sentences. This is what defines the structure. Yeah, it says nothing about the meaning. It says that this is a right sequence, this is incorrect sequence in terms of this language. Grammar is the way to express the syntax. So the most well-known example of syntax, predefined syntax, is the book on Russian or English grammar. So this is what actually a formal the code for writing in the language. If you study it through like 10, 11, 12 years of your school, you know how to write in your language. There are more formal models like formal grammars, and they also define how to form strings from some language alphabet. So we can call alphabet what? If we speak about collecting words from letters, this is an alphabet and the language of words. If we speak about the language in more common understanding, in our understanding, like English or Russian language, the alphabet here means the vocabulary. So the set of all words which you can use. Yeah, so and how collect sentences from words. Okay, and these rules should be like formal and should be writable in some notation. In mathematics, the term formal language, which can be described with formal grammar, is a set, just nothing, just a set of all allowed words, all allowed sentences, which satisfy those rules, as well as those grammars. And this is a tricky thing. So if you say there is Russian language from mathematical term, from mathematical point of view, it means this is the potentially infinite collection of sentences, because we have the like complex sentences, we can put comma and write and continue, comma and continue. So our sentences are potentially infinite in length. They are potentially infinite number of sentences which you can build. That's why no one ever enumerated the language, except maybe some toy examples when the language is simple and you can write down all possible sentences. In other cases, the language is enormous, yeah, and the task of NLP, the task of computer linguistics, the task of compilers, which work with different languages, is to generate and recognize sentences according to grammars. Okay, so if you do, like if you generate the code, you want to generate a correct sentence in Python. Yeah, if you generate the code or you generate language or Russian language, GPT-3 should generate the syntactically correct sentence in English. If you recognize something, if you're given a sentence, the compiler should be able to parse with respect to grammar and say, is it a correct sentence in Python or not? Yeah. If you say it in Russian, if you want to know which roles are given to each word in sentence, is it a correct sentence in this language? Formally, the grammar is defined. Like I saw some definitions with 5 terms, but the grammar can be built using these 4 sets. So the first set of terminals. In our case, if we speak about natural language, these are words which we use, like cat, dog, run, Stas, I don't know, all these words. Non-terminal means the grouping of words, some aggregation of terms. So for example, I can, for language, the most well-known groupings are verbs, nouns, adjectives, because they behave similarly in similar contexts. If I say that you can put an adjective before a noun, yeah, you understand that this means I can say red Stas, fast Nastya, hungry Lisa, and so on. Yeah, so these things are generalizing the rules. Okay, So non-terminals are aggregations. We can go and build hierarchy of non-terminals. For example, I can say there is the verb phrase. So this is the combination of verb together with adverb, running fastly. Yeah, all together, this is again the action. This is not just a verb, it's a verb phrase. And this is again non-terminal, which is consistent of a verb and an adverb, which are both non-terminals. Okay, and you can build pretty big hierarchies of these non-terminals. Productions. Yeah, the question. What's the difference between non-terminals and sentences? A good question. When you speak about, let's say, Python, a very simple example, is a variable name a correct statement in Python? Yeah, it's a non-terminal variable name. So you cannot split it, it's a variable name. Is summation a correct part of language? Yeah, it's non-terminal plus another variable name. So something plus something equals something. Yeah, this is the condition. Yeah, but in some languages like C, for example, if you write something like this, it will lead to compiler error because it says that you gave me some expression, but this is not an operator. Because in this language, there should be an operator, something which performs an operation. And if you say A equals B, what's the use of this operation? So it doesn't change anything. And some languages will allow, as I don't know, C. Or some languages will disallow such constructions, as Java. Java will disallow you just to write a comparison. Yeah, so it will be a comparison, a non-terminal, which is valid in terms of language. But to be a part of like a sentence, an operator in Python, let's say, you need to write what? If, condition, column, result. Yeah, and this will be a correct operator, a sentence in the language. Like in Russian, you can say fast stas, and this will be not a sentence because what you want to say. So what am I going somewhere? Am I sitting on a chair? So what's the statement? So non-terminal is the part of a sentence which is valid, but doesn't mean the statement of this language. So you can at the model you define these are sentences. These are still not. They are smaller than a sentence. And there is a special non-terminal called start symbol S, which is actually a combination of some non-terminals and terminals, which is a sentence. If your string matches with this start symbol, then perfect. You parsed a correct sentence in Python or English. The question? You want to comment? Please speak louder.
For example, if you have an instruction, the word if is terminal, but the condition is non-terminal. So you can't put any condition. So it's not terminal. But the if word is terminal.
The if word is terminal, I agree. And then?
And the condition is non-terminal.
Condition is non-terminal, I agree. You can combine terminals and non-terminals.
So the sentence is a combination of non-terminals and terminals.
I will show you the pictures. Sentence is actually a tree. And in the leaf nodes of this tree, they lay terminals. And the internal nodes of this tree are non-terminals. This is how it usually a result of a parsing. I will show you the picture in the next slide. So I want to just to enumerate these parts of the language, so how the grammar is defined. Terminals, non-terminals, aggregations of non-terminals, starting symbol as the idea of at some point, these non-terminals should join into a valid construction, an operator in programming language or a sentence in a natural language. And productions are actually just the rules saying that you can combine the words like this and you cannot combine the words like this. So, and productions, they are about allowed operations, saying that these things are potentially possible in the language. These things are impossible. So they don't say which is impossible. They don't just list impossible operations. So here is the, there's a person called Noam Chomsky. What is your pronunciation? In Russian, like he was originally from the Slavic country, so the correct way in Russian will be Chomsky. He is known to be a very good, like the most well-known maybe linguist in the world. And he proposed the idea of structural linguistics, which says that we can define whatever we say, whatever we write down in the language, in some formal way. And this is very important, because if you can formalize the very informal thing like a language, you can start working with it as with data, not with just the letters, but now the structures. And then any text mining techniques can appear, any analysis, automatic analysis of text can appear. And he provided the hierarchy. And this hierarchy, just for you to understand what's the idea, starts from the most free languages to the most constrained. So the most free idea is a recursively enumerable language, which says the following. So we can write any kind of production, which means that in the both left and right side of production rule, so what can be combined into what, you can write any combination of symbols, which lead to what? So whatever terminals you have in the language, any possible combination of these terminals are allowed. So your language is just like a Cartesian product of your terminals. So whatever is allowed is allowed. Yeah, and that gives you nothing, because you cannot analyze the language if anything which is built of terminals is a valid sentence. Yeah, there will be multiple ways of parsing the same sentence, a lot of structures which show how the sentence is generated from the terminals. So very unuseful concept, which is still need to be here in hierarchy to express the most free idea. The next constraint is context sensitive. And here we come to actually natural languages, but this is, how to say, this is what we usually try to avoid in parsing natural language. Because context sensitive languages, so here I want to just give a small explanation. So the big letters here mean non-terminals. So for example, verb, yeah. Small Greek letters mean terminal symbol, some specific terminal symbol. And what does this phrase means? It means that the meaning of this word, like meaning the part of speech, for example, of this word, the non-terminal for this word, depends on the context. So just a simple example. If I say brown beer, the word brown in this context becomes what? An adjective. Yeah, so brown beer. Beer is an animal, and adjective is the characteristic of an animal. If I say Professor Brown, the same word brown becomes a surname, yeah, which can be treated as noun. Yeah, and that means that depending on the context, the same word, the same terminal, gamma, here Greek letter, will be treated as a different non-terminal. And if we create such kind of productions, we have lots of situations in which we need to consider the context. And this means the parsers which we use are very complicated. So we need to always think about the context of the word. And this is the very hard concept for programming. The simpler form is what is actually not the real language, the real natural language. But we use these models for parsing natural language. So we oversimplify the real world. This is a context-free grammar. And context-free grammar says the following. So context-free grammar allows you to have only a single non-terminal at the left part. What does it mean, left part? So there is a actual part of sentence, yeah? So some sequence of words, and we will treat them later as some non-terminal. So when we parse a sentence, we do what? We detect such a group as on the right, and then we reinterpret as the non-terminal, and we will use it later as a group. This allows us to do what? To shrink the sentence. Each time we replace a group of terminals by non-terminal, the sentence is becoming shorter, 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 until it reaches the state of just a single non-terminal sentence. Yeah. So that's how the parsing procedure goes on. And context-free grammars allow us to get rid of context. And the most strict form of a grammar is a grammar which not only allows regular, also allows a non-terminal here, on the left, the single non-terminal, nothing else, but also restricts either to non-terminal after a terminal or vice versa. So the right regular grammars and left regular grammars. So whenever you say the production can be of the form, the verb phrase is what? Is a verb plus fastly. Yeah, this is allowed, but you cannot say fastly verb. So you cannot write such kind of productions. So the very restricted number of types of productions. So they are just only a non-terminal is a terminal, or non-terminal is a non-terminal plus terminal, allows you to do what? Each time when you parse or when you generate a sentence, you do what? You, by this type of productions, you just append a symbol to the right. What does it mean? So there is some already parsed part. You have another next terminal in the sentence, and then you look for productions which meets this condition. So non-terminal followed by this word, you can glue it to the non-terminal, and you continue. So you can parse sentence from the first word and continue going to the last word just by eating one symbol at a time. So you parse them in linear time with respect to the length of the sentence. So regular grammars allow you to build what is called the finite state automaton, this thing, which will, with each symbol or with each word, proceed one step further, and it will converge in the end. So this is how, for example, the numbers are parsed. So you see this is the language of floating point numbers. The words are symbols, such as digits, punctuation, and E letter. So this altogether is the language of all possible numbers you can write down, yeah, in programming language. And each time you get new digit, you move forward one step, and you will end up here or here with a number. Or if you finish before, if the digits they exhausted and you're still somewhere here, that means that you didn't achieve the correct number. So something ended earlier than expected. So just an understanding that this is how the languages are perceived by linguists. So there is a set of rules which you can write down. They are formalizable, and they allow to do what? To actually build a structure of language. We will see how it looks like. But before this, in programming, to write down production, there are some languages. So one of the most widely used and known, this is the Backus-Naur form, BNF, and extended Backus-Naur form, which allows us to write these kind of productions with arrows, which Chomsky proposed, to write them down in some code. Yeah, so the extended Backus-Naur form is the way to slightly generalize things, and it allows you to write down these productions shorter, so in a slightly shorter form, rather than writing them in the Chomsky way. And this, I love this joke, but no one usually smiles, that extended Backus-Naur form was proposed by, obviously, whom? How do you think? Backus-Naur? No, it was Nicholas Wirth. Just a joke about the naming, that this naming is not exactly correct. And what we get, so being able to write down the productions in this form. So you see that there is non-terminals, and there is so terminals and non-terminal here, and all they are non-terminals here, and some productions here, meaning that the determiner is either the or a, the noun is chef or soup, the verb is cook. Yeah, the noun phrase is what? Is a determiner plus noun. Verb phrase is verb plus noun, or verb plus noun phrase. And the sentence is a combination of noun phrase plus verb phrase. That if we apply these rules to our sentence, we can detect the places in our sentence which match the rules. For example, in some place we find the word the, and we say, oh, we saw a production here. So we see the word there. We see production which can convert it into a non-terminal, and we apply it. The same with soup. Then we see a rule which says that if determiner is followed by a noun, we can convert this group into a noun phrase. Yeah, and we call it noun phrase. And then we do aggregation, and for practical needs, these algorithms of aggregation can be heuristic, but actually they are exponentially hard task to find this tree. In the language, like as we understand it in natural language processing, the language, the sentence will always end up with a tree structure. Okay, so we speak about syntax tree. The syntax AST, abstract syntax tree in programming language, abstract syntax tree in natural language. The difference is that in programming language, you will, as this is a regular language, you will always be able to end up in linear time for a compiler. In natural languages, unfortunately, the algorithms are more complicated. And this is how we can represent a sentence based on very formal definition, a grammar. And what it gives us a very important thing, which we will speak about later, that now any word in this sentence, or maybe the combination of words, they not only a part of a big story about the structure, they also grab some attribute. Yeah, so this attribute is the role of this word in the sentence. So now we don't have just a word. Now we have the word plus a role. Now we know that this is the Brown adjective or Brown name. Yeah, so these are different roles, and this knowledge is very powerful. Yeah, so and we will see how this power can be used. So I hope that at least here you understand the general idea. So the language has a structure, the idea of Chomsky. These are the tools which you can use, the parsers which you can use to get this structure. And this structure provides you what? The roles of words in the sentence. Okay. One of the important tasks which is done in the initial step of compilers and in when you process the text, even before creating maybe a structure, is a tokenization. A token is actually what? Is a combination of lexem, the word itself, the non-terminal. Yeah, the question? Not meaning, but the role of the word. The role, which role it plays. For example, if the soup would be here, it means that the soup is an actor in this sentence. So the soup, I don't know, is going for a walk.
Isn't it just lose idea of the context? So we not really use it because it depends on the context. Role of the word.
The role of the word depends on the context. Yes. In this structure, we don't use any context information. This is wrong because of, again, as I mentioned, there are two nouns here in this sentence, which are in some particular places of the sentence. If we swap them, their role will definitely change. How can we see this? How can we see that the role changed? We can go up by the syntax tree, and by examining the nodes here, I don't say that this is like the 100% only way of determining the role, but we see here that this particular noun is a part of noun phrase, which in Russian is like mostly mapped to подлежащее, so the actor of the sentence, who is doing something. Yeah, and here we see this is chef or chef, and this one is behaving as the dependent word in the verb phrase. Yeah, so the context is not linear here, but it's a tree-based context. So here you see that as this word is a part of verb phrase, this is the dependent verb. In Russian, we have additional information in terms of flexions, because we have what is called падежи, which we don't have in English. So where the same word can even be written in a different way in different position. But here we cannot distinguish them, and the only thing we use here is a context. And the context here is actually what? Is this. saying that we meet the determiner together with noun. We need a verb together with noun. And in this case, noun will be a dependent thing. And in this case, noun will be like an actor. I hope I answered the question. So, but this is actually all this information is secondary with respect to what we explored today. So tokenization, important thing, splitting the sentence or an operator into parts. A token is a combination of a terminal symbol, like the word from vocabulary, and the role which this token plays. In some cases, this can be, like the role can be obviously derived from the terminal. Sometimes you need to add some computations. And here syntax can help you with determining the role of the lexem. So here is the example of parsing of tokens for some particular sentence. And there are sometimes problems which can be on the way. So this one is the obvious situation, but what will happen if you look at this slide? So why syntax parsing is important? Syntax is the simplest way to extract the smallest meanings, which are not actually meanings, but they are like roles. You add some semantics to a word, but not in the general term of semantics. To the smallest lexical elements of the language. Yeah. So the lexical element is what is unparsable, unbreakable, the word. Yeah, the word. You cannot break the word into parts. It will lose the meaning. But the word itself holds some semantics. And syntax parser is important when we speak about bringing the text into parts of these lexems. Yeah, because some cases are complex. For example, here, like the French, yeah, sometimes the words by the syntax of the language, they glue together in a single string. Yeah, and you need to separate lexems. Yeah, in Russian, this is not usually the case, but in English, you know that there's a word cannot and there's a word can, and they actually opposite by meaning. So you can either think this as about a single lexem or just a glued lexems together. Sometimes the language has no spaces. You just cannot do, I don't know, string dot split in Python and bring this into lexical elements. You need to apply some knowledge about the structure of the language to split this into, I don't even know what is this actually, but this is some sentence which I don't know how to parse into words, because I don't even know, is this the words, letters, or whatever. So maybe this some combinations of hieroglyphs are forming the word. They like by 2, by 3 of them. Arabic language, like I always love this because I went to United Arab Emirates and I learned that Arabic numbers are actually not what we used to call Arabic numbers. So Arabic numbers are different. There are some of them similar. Maybe, I don't know, but I know that the direction of writing is from right to left, yes, and the Arabic numbers from left to right. And when I look at the sentence, I understand that reading is not that easy for me. So I used to read from left to right, but I read from right to left, then I stop, read back, then jump, then read back, and this is like mind-blowing. That's why tokenization, like this is a simple example of how to use NLTK to take a syntax parser to do a parsing into parts. So you involve the syntax of the language, you involve the grammar of the language to split it correctly into tokens. This is very important because we will work with tokens later. Okay. Also, so for now, I want to just you to concentrate on a very important idea. So language, smallest item, the lexical element, the language unbreakable element, is a terminal symbol, the token together with the role which it plays. And the technique which we'll consider later, the inverted index, is based on analyzing and storing these elements, these smallest parts of the language, the tokens. Unfortunately, if you take Russian language or English language, you will observe that the number of unique tokens in the language is enormously big. So if you take national corpus of Russian language, it will give you 3 million of different elements, or maybe more. Even if vocabulary, like a dictionary says that the Russian language has not more than 1 million of words, the practice of use shows that the words appear. There are some once used words. There are chemicals like the names of chemical formulas, which are very unique and they can be constructed, and they will be just a normal Russian word. But unfortunately, there is a potentially infinite number of such words. Yeah. So the number of tokens is very big, and if we think about the fact that the number of tokens can be even bigger than the number of texts which we will want to index. So if you have millions of tokens and you have like thousands of texts, this is not that easy to build a good search engine. And there are multiple, like, how to say it, crafted techniques which were tested by time, which I used to bring down the size of terminals. So yeah, now we have the vocabulary of language. Now, next time, we need to do what? We need to make it smaller. How to do this? How to make the vocabulary smaller? These techniques which you can meet in practically any NLP solution. So first, we do case folding. This can bring to some ambiguities, as with the word brown. So brown with a capital letter B and with a small letter b will glue together. So we will lose some information here, but we are ready to pay because majority of capital letters appear where? In the first letter of sentence. When you do parsing of sentence, the first letter is capitalized in Russian. In English, it's not the case in other languages, but in the European languages, the first letter is just capital by the fact that it's in the first place in the sentence. And if we take all the words which were ever in the first place, we will double the vocabulary. So what we do, we first reduce this thing. This will bring to some problems, but it's okay for practical solutions. Next thing, languages have flexibility of terms. In Russian, we have times, we have падежи, we have all the stuff, which allow us to write the same word with the same meaning with respect to some context in a different way, like here. So this is the initial form of the word run, and this is I run. Yeah. So again, in English it will be the same word. In Russian, this will be different words. In English, there is the first form of the word compressed. So it's which can have different variations. So for example, the word can form a noun, the word can form an opposite word, and so on. So usually variations of the words is managed by flexions. So prefixes, postfixes, so all these flexions. And to remove this variability of language, we apply one of the techniques. We either use stemming or lemmatization. Stem, what we call a stem, this is a stem, the basis of the word. In Russian, it's called основа. So the part which is not changed when flexions change. So we extract the stem. It can be not a real word if we extract it. Yeah, so it can be the part of word, which is not the part of the language, but we can reduce all the words which has this stem and some flexions to this stem. Okay, so this is the technique which will produce some strange subwords without variability of context. The second, and of course here you can lose some information. So if the flexion was changing the meaning to the opposite, like compress and uncompress, it can have some, again, lead to some loss of information. Again, in practice, this is usually not considered. Yeah, the question?
Is like libraries for stemming, they have some dictionaries.
The question, libraries for stemming, do they have some dictionaries or not? Actually, they have combination, because if you know that there is the 3 million of words, if you have a dictionary of all these words, you will have what? You will have at least a binary which stores like at least like 10 megabytes of data. Yeah, and you want this library to be fast and good. And of course, these libraries, they store the dictionaries of some hard cases, but some things are algorithmic because the language has some repeating patterns. For example, here we have the flexion of Russian verb, which always in the initial form is finished by T and мягкий знак. So if you detect this, with a high chance, this is the gerundi, like the initial form of the word, and so on. If you have ion in the end of the English language, this is the verb which is produced from French, and this is the verb, and you can cut ion from here to obtain the stem. So it's algorithmizable, but this leads to what? So you need either to grow a vocabulary or to write more complicated rules. And in the end, all these libraries, they do what? They do mistakes, unfortunately. And you can go to any website of a good library like Spacy, like Natasha, like PyMyStem, and you will see that they compare and they show like the rate of 90-something% of accuracy, meaning that they do mistakes. But the other technique is to do lemmatization. Lemmatization is just bringing the word to some initial form. So instead of taking the stem, it brings the word into some initial. Both techniques are okay. Stemming is more, how to say it, more strict. So it's more hard and accurate because it will bring different types of parts of speech into a single stem. Here, the part of speech will be preserved. So, for example, Yandex in its internal implementations uses lemmatization. So it converts words into original forms, not to stems. Okay, what else? Stop words. I will show you
which one is better. Which one is
better?
between
There's
them?
no correct answer. So again, depending on your task. So the stemming will bring the vocabulary to a smaller size. The lemmatization will be less that strict to verb, so to word forms, to parts of speech. Again, depending on your task. So I used both for different tasks. Maybe one will lead to errors. Maybe one will lead to some misbehavior of your code. Just choose at the run, so whatever you use. Other technique is using stop words. Some words can be useless. Useless in terms of how to say it, selectivity. If you want the search engine to judge a text by words it uses, in any text in English, you will see what? Determiners the, word to, and so on. Yeah. So they will always appear. They will be always are. They will be always, I don't know, is, and so on. These words will appear and they will bring no additional information. They exist in this text. In Russian, это, or который, and so on. These words will appear in any text. Yeah, and they are usually addressed as stop words, and they are just removed at parsing stage. So you don't want to work with them later because they will meet in any text, and that means that if you want to index something by this word, that means that all the documents will be attributed to this word. This will bring additional information to your system, and you don't want this. And also thesaurus and synonyms. So if the words, they have the similar meaning, if you want to glue some words by the meaning, like fast and rapid, you use synonyms to glue the terms. This usually requires hand-built dictionaries. Okay, so let's stop here. We have 17 minutes left for explaining the major topic of this lecture. Well, we know what is language. Language is a set of terminals, so of all possible sentences in the language composed of terminal symbols. Syntax is the lexical term, linguistical term, which says what? There are rules of building sentences from terminals, and grammar is the way to express these rules. The grammar, the formal grammar, is how we write down these rules. There can be a book of Russian grammar on your table. There can be a file with this formal grammar in your computer. The formal languages, there's a hierarchy of languages. And there are techniques which bring down, like explode your sentences into the smallest lexical parts, lexemes, which sometimes require syntactic analysis of the sentence to bring the correct attributions, and also to maybe correctly parse the sentence, because languages are not very simple. The Russian language is pretty simple. If to split words into parts, you just need to parse it by spaces and punctuation. There will be some hard cases like the dash, so 2 words which are connected with a dash, but you can compute it as a punctuation. We have no apostrophes, nothing like this. And in other languages, things are much harder. And syntax, the rules of constructing the sentences, can be very useful for tokenization. And now we know that there are some techniques of reducing the vocabulary. After we exploded the sentence into parts, we can even reduce the vocabulary to make it smaller, more practical, by applying techniques which all of them bring some ambiguities to the language. So it glues together adjective Brown together with surname Brown, but in general, they do much better job in terms of reduction. So the profit from reduction is bigger than the bad effects from gluing things together. Okay. A few words about the topic, which is described in your books. If you want to go there and read the article, like there's a link to the book, which is the major book of the course, Boolean retrieval. So the concept which we'll apply later. So the idea of Boolean retrieval is the first way of how we retrieve documents. The first idea is that, okay, there is the search which solves what? Solves your need in information. You want to solve your need by not just some words, but by a meaning of the text. Yeah, so the text means the answer for your question. The text means what you want to learn. And the smallest lexical part, which can hold the semantics, is a word. Okay, so we will base on the smallest lexical elements of the language to at least give you a chance to find what you search for a meaning. And then we say, let's consider a document as a bag of words. The model of bag of words, you should know it from the machine learning course. The idea that you take the sentence, split it into words, and then you say, this is not a list, this is the bag, a set. Yeah, maybe a multi-set, how you treat it. And then you don't care about the order, you care about that these words belong to this sentence and don't belong to this sentence. So this is the bag and bag, okay? And Boolean retrieval says what? We will consider a query as the intersection question. Does this word belong to this bag? If yes, we will take this bag and consider it later. If it doesn't belong, we not. Then we can build a long queries, which, for example, all connected with end word. And we will do what? We will retrieve all possible bags which has the first word, the second word, and so on. And then as they use the Boolean term end, we will do what? We will do intersection. We will find which bags hold all 3 of them. Yeah, this is the Boolean idea. The Boolean queries can be more complicated, saying that it has end, but it also has not somewhere, or it has or somewhere. And then the actions we perform with these bags of words will be corresponding. So if not, we will negate the sets and so on. So the Boolean retrieval is what? Is retrieving the documents based on the term and then applying some Boolean operations to results. Another thing which I wanted to say that this is my observation, it's not written in the book, that any search engine or recommender usually follows the same technique. Any Boolean retrieval, ranking, nearest neighbor search, whatever, requires what? To match the term or the phrase to all the documents of the collection, all the elements which you want to search for. If you do it in linear time, it can be very expensive. Yeah, so it requires some indexing, so building some additional data structures, which will help you to do it faster. But if you do an exact search, that means that anyway, if this is an exact search, you should be very careful in what you retrieve. There should be an exact index, which will allow you to bring things on top exactly. Sometimes building such an index is impossible. So sometimes your index will be approximate. That's why usually systems, any system doing Boolean retrieval, nearest neighbor search, exact range search, and so on, they do a pre-select phase with a the phase of exact match. So pre-select means what? I want to search for a, just imagine, I want to search for a phrase Stanislav Protasov in some texts. If I follow the idea of Boolean retrieval, I will split this query into two requests, Stanislav and Protasov. Okay? Doing a Boolean retrieval, I will do what? I will retrieve the documents with Stanislav. I will retrieve the documents with Protasov. They are bags of words. They don't care about the order. So what I will have an intersection of documents which both have Stanislav and Protasov. Wonderful. But I'm looking for a string Stanislav Protasov. And I will need to do what? To rerun the search in this smaller collection to look for this exact substring based on the exact content of the query. Okay, so meaning that most probably in any search engine you will meet these two phases. First, we'll pre-select you the documents which are candidates for result, and then you will do something, either exact match or re-ranking of the documents, which will do a better job on a smaller set of documents. Okay, and now we have 9 minutes to express the major concept of this lecture, text indexing. So how can we, based on the concept which we learned, the lexems, the tokens of the language, and the need in speeding up the process and in task of Boolean retrieval, how can we do it fastly? And the answer is this. This picture is taken from the book, which is called Computer Science in the Real World. It's publicly available. It was published in CMU, Carnegie Mellon University. Originally, the idea belongs to the god of the books in computer science, Donald Knuth. Do you know him? It's the author of this multi-book encyclopedia of how to write good programs. And the second book, I think in 1960-something, he proposed the idea, which is now known as inverted index or inverted file. And the idea is very simple. First, you need, given a collection of documents, which can be what? A distributed set of documents on your computers, a set of documents on your machine, whatever, build a lexicon, a vocabulary of this data set. So all distinct words which you are interested in. As I mentioned, you can do what? You can just split the text into words, or you can do more sophisticated technique like stemming, like removing stop words, and so on, so on, so on. So building lexicon is a step in this procedure, which can be implemented in different ways. After you do this, after you obtain the lexicon, you create what is called posting lists. So this is the term from the book. I will reuse it. The posting list is what? Is a collection of documents which has this word inside. Which have, yeah. So each document in this collection is a single posting list, which is usually a linked list data structure. This collection is stored somewhere. You can imagine this as what? As a hash table. Do you know what's hash table or hash map? So the key here is a word, and the value here is a set of documents. And these are usually not the documents themselves, of course, because the size of the documents is pretty big. So you cannot store the documents in memory. but you store the pointers to these documents. That, like in terms of web, this can be URLs. Okay, you store the collection of URLs which lead to pages which lay outside of your computer. And when a person wants to retrieve a document, what person does? Person writes down the query. Here is the, let's say, squirrel. Yeah, so this goes to, as a key to a hash map. This returns you what? A set of documents which has the word squirrel. And these are not just documents, but the pointers to documents. And then a user, by this pointer, can retrieve these documents from different places, from web, from somewhere. Okay, so what does it mean? The search of the key is a constant time if you speak about hash maps. Yeah? Or if you use tree maps, it will be a logarithmic time, still fast. Then you obtain the set in this time, and then just the time of retrieving the documents but given a pointer. It's just about the loading time, which you cannot reduce. Yeah. So this is the overall technique of search. In some cases, this index itself can be a big one. So this part lays on the hard drive. That's why it's very important to persist the elements. But in practice, today, in my practice as a person who worked for search engine, I say that this is a very useless technique, because if you want to search fastly, going to the hard drive is just very, very expensive operation. That's why these indices are better saved in RAM. Okay, but if you want them to be stored on the hard drive, there is, of course, the chapter in the book on this. You can read how to do this, but the idea is exactly the same as storing sparse matrices on the hard drive. If you ever learned about how to store sparse matrix in memory, we do sparse matrix, the matrix which has lots of zeros inside. So the information is only appears somewhere. So the sparse matrix allows you to compactly store it in RAM, and the same technique is used in posting this, how to store the sparse matrix on the hard drive and to obtain the collection of documents in a fast manner. So this idea, the inverted index, is very simple. So you invert, why it's inverted? Because instead of documents containing words, you use what? Words containing documents. And that's why it's inverted. Yeah, that's the inversion operation. Oh, sorry guys online. A small comment on lexicon building. So of course, the world is much more complicated than we usually think about it. The language has a lot of names and phrasal verbs, phrases, which consists of 2 and more words, like New York. And using big RAMs in this lexicon, using some statistical techniques to find things can be very useful. Another thing, that tokenization itself brings you only the words which are in the collection, but it says nothing about the words which are in the query. Yeah, so you will retrieve a document, but you type the word which is not in the collection. And if, for example, when you were building a vocabulary, you didn't consider such words, what can happen? You can consider them as outliers, as typos, and so on. You never saw this word, and you remove it. You don't know this word in the Russian language, you remove it. You use stop words, you remove them. You use numbers, you remove them. And in today's models, and we will speak about this later, there are techniques how to deal with this. This is usually subword tokenization. So instead of only working with lexems, which means something, you also work with subwords. So you take the word and split it by 4 characters with overlap, saying that the word Stanislav will become Sten, Teni, and so on. So these subwords will be also indexed. This is not that many of them. So if you take three-letter subwords, it will be 26 in power of 3, around 30,000 of additional words. But this can allow you to search for documents for unknown words with unknown syntax, unknown semantics in texts which can have such words. Like we will speak about out of vocabulary problem in the next lecture. And also stop words. Stop words depend on the context. Somewhere the word can be considered as a stop word, somewhere not. Simple example, imagine the texts where lots and lots and lots of lists are given. Yeah, so some, I don't know, recipes or whatever. So you enumerate the steps, and there will be numbers, and there will be lots of numbers, 1, 2, 13, 45, so on. And these numbers can be useless because they appear in any text. The word 1 will appear in any text. Yeah, but if we speak about historical texts where the dates are important, you will not be that sure that numbers should be stripped out of the text. And that means that stop words should be also carefully selected for a particular problem, what you actually index. Okay, and here I want to point on the problem which we will consider in the next couple of lectures, and which is the result of what is called Zipf's law. There is a law, empirical law, that's why it's not a theorem or hypothesis, which says the following: the frequency of word occurrences in the text is proportional to 1 divided by rank of the word. So that means that there are words like and, the, to, and so on. They will meet, they have the rank 1, for example, and they will meet in any text. The probability of seeing them in the text is 1. There is a word which is twice as like the rank is, for example, I don't know, 2 or something. They will be seen twice as frequent in the text. And the less frequent is the word, the probability of seeing it is 1 divided by rank, and it goes down. Zipf's law gives you this picture. There are some words, the stop words here, which will meet in almost any text, and using them in queries and indexing will be a pain. If you just imagine the inverted index, what you will see? You will see the word to, which has a posting list consisting of all texts in your collection. So it's very useless to use this word in indexing, because when you will do it, what will be the search procedure? You will search for the phrase to be, yeah? And for example, to be, let's say, to be Nastya, yeah? What will be the procedure? You will search for to, be, and Nastya, and you will retrieve posting lists of these 3 items. And the posting lists for to will be all the documents. Then posting lists for B will be all the documents. And Nastya will be like 3 documents, for example. But first you need to store these elements in your memory. Then you need to compute the intersection of these sets. And you will spend a lot of time on retrieving this information. And the result will be 3 documents. Yeah? And it means that 2 and B have less differentiating power. And Nastya is a good word because it takes the small amount of documents out of the big amount of documents. That's why stop words are removed. They are bad. They are noise for search. They requires you additional computations and storage. There is also another thing. There is the long tail in Zipf's law of words which are met in any millions of documents, one out of million, out of 10,000, and so on. And unfortunately, there is a pretty big number of such documents. And if your vocabulary will store all of them, the size of your hash table will be big. And they will be like a word with a single document, a word with a single document, a word with a single document, all of them. So additional memory in index just for storing these words and storing posting lists for them. And practically no need, because if the words are like not frequent, usually users don't use them in queries. They are not frequent. And this will be the problem. You store additional memory, but you sacrifice it for nothing. So no practical need. And that's why less frequent words are usually also removed from vocabulary. And these, which remains, has some differentiating power. The words which are not that frequent and not that rare, which can, each of them bring you around, let's say, a square root of number documents from the whole collection. This is the problem. The problem also says that with the increase of the collection, the size of all collection of documents, these absolute values will also grow. Yeah, so it will be not 800 but 8,000, 7,000, and so on. And that means that the sizes of posting lists will grow, which leads to what? That the inverted index file is not very scalable. If you want to use inverted index file to index 100 billions of documents, be ready that the posting list sizes will be millions of documents. It means that intersection will take a significant time. Yeah, and we will speak about how to overcome this next lecture. Some notes on this. I see that we 4 minutes ahead. Should we continue or should we stop for a break? Let's stop for the break. So I will finish this lecture after the break. Let's meet at 10:55. Yeah, in 10 minutes. Great? Great. Mohammed is here. Mohammed,
Yeah.
yeah. Are you there? See in Zoom.
Yes, I'm here.
Great.
Yes.
Кирилл Данякин. Кирилл. Видишь, да. Такая тишина. Вы живы? Да, я не услышал. Эдл
Okay.
No, great. Денис Фокин. Хадиджа is here. Роман Гараев. Вейгу here. Ikrам. Twice. I see you twice.
Yes.
Oh, and I can hear you twice. Okay. Firas. Елизавета. Далер. Сою. Ярослав Плаксин. Туточки. Герман Тарасов. Тут. Айдар. Тут. Можете не убегать сегодня в 12:00 по зову еды? Хорошо. Данил Зашихин.
Yeah.
That's you.
Huh?
Вот это вы, да? Хорошо. Здрасте. Смысл просто посещаемость. Да. Мне кажется, что были ситуации, когда вас не было.
Я не был.
Вот. Я тоже. Okay. Okay, so I'm still recording. Attendance is checked. Everyone is here. You're perfect. Please do the same for the next 4 lectures. And we continue with the lecture. Boom. Boom. So what I wanted to say here, so it stopped sharing for some reason. Great. So just a second. Okay. So few notes here. So from my personal experience, external memory dictionaries are not that efficient, as I mentioned. A simple example is that the requests and how to call it, the features which are needed from current search applications. If previously waiting for 5 seconds was totally okay, today, as I mentioned, as I showed you in the video, the upper boundary for search time is around 1 second for any service. So it means that if you use hard drive, you find yourself in some situation where the majority of time will be spent on reading from hard drive. And that's why in real applications, which I saw, the files are usually used for memory mapping. So files are used to deliver the content of index to a machine, and then just memory mapped to RAM and used in RAM. So the way how the data is organized is mostly important for fastly using it in RAM rather than fastly using this in a hard drive. Second, today, building an index, all these procedures as tokenization, building this dictionary and so on, requires a lot more memory than the index will take in the end. So that's why even the index can fit into a single machine. The infrastructure to build it can be much bigger. And you can maybe face this in your labs just by seeing how much memory you need in process of preparing the index rather than for just storing it. That's why today MapReduce is widely used for preparing indices. So doing like the parallel and streamed operations for building indices. For today, indices which I used in practice are mostly static. It means that you build it once and you use it for some time, for a day, for a week. But to be fast, these indices need to be prepared in a fast manner. Today's data structures, they are unfortunately not very good in self-balancing at the run. Inverted index is okay. It can self-balance. So you just insert new document, you just write the link into all the occurrences of words, and you just continue using this. But other data structures are not that flexible in terms of updating. That's why today the indices are usually consistent of the big index, which stores the state of the system, and then some updates for the changes in the recent time. And then you just merge these changes into data structure, you rebuild it because it takes a lot of time. If the number of documents is too big to store the index on a single machine, you can use just sharding, a simple technique. When you use, you split the collection of words into those which from A to C, from D to F, and this is called sharding, the horizontal scaling. You can do it hash-based, so because when you do it splitting by letters, you cannot guarantee the balance of documents for each shard. So doing it by hash makes it uniform. So if you compute the hash of word, it will be most probably uniformly distributed for all the words in the documents. And also a compact form of storing the index, the words, is a trie data structure, which is sometimes used to store a big set of documents on a single machine. So if you want all the words, like the billions of words, for example, stored on the single machine, a trie is a way to compact it, because the size of the trie is usually not that big. So it reuses the paths in the tree. If you read about trie data structure, you will learn that it reuses the paths to store the same, like words with the same prefixes here. So it's very useful to store big sets on a single machine. There are other techniques of storing big sets. For example, I don't know whether you had the algorithms courses or something else, but Bloom's filter. You know Bloom's filter. If you want, you can read about this. Like Bloom's O filter is the way of storing a big set of something with a very small limited size of memory with some maybe false positive matches. So if there is no element in the set, but it will say it is in the set. So Bloom's filter is used, for example, in your web browsers, in Google Chrome, to store the collection of potentially dangerous websites. The number is big, so you cannot store the list of websites. They use Bloom filter with potentially false positives, which then reject in the servers of Google. But in your local machine, it checks if there's no website in this set, it will just let you go to this website without any communication with servers. Otherwise, it will recheck it in Google site. So another way of storing big set in a small set of memory. So trie is another way. Fastly look here. How to map certain Boolean queries in inverted index using this paradigm of pre-ranking and ranking. The same example I showed with Stanislav Protasov. You build a Boolean query, you build the set of candidates using Boolean operations with sets, and then you recheck the documents in the last step. Yeah, this is how we can search for a string, substring in such index. Okay, what is wrong with Boolean retrieval model, no matter which index we have? The query is very hard. It's very hard to build a query in a precise manner. It can be over-constrained when the terms are too specific. So, and you lost them in building the index, you will retrieve no documents. Yeah? Other thing, if the words are too general, like very frequent words, you will retrieve a lot of documents. They will not satisfy your information need. And to find the right place between over-constrained and under-constrained is sometimes a trick which is solved by a user. So you need to rephrase the query to obtain the document you need. Yeah. So this is the task which can be done by a machine, but is done by a user, which takes time. So we need to do something different. Also, even if we speak about information need, we understand, you remember there is a term called intent, your information need. And when you project your information need into the query, the same query can come from different intents, The same intent can go into different queries from different users. And relevance here will be different for the same document. Even if you return the documents which include the word, it doesn't mean this satisfies information. It is irrelevant to you. So relevance has a scale. Relevance is a matter of degree, means relevance has a scale. So for any of you, it's not absolute values. For any of you, it can be slightly different. So how can we deal with this? So what is the, how to call it, alternative to a Boolean retrieval model, which is either under constraint or over constraint and doesn't think about your information need? The other thing is doing a ranking. The general idea is the following. So if you say about documents, whether they are taken into the result or not taken, you speak in terms of Boolean retrieval model. You divide the documents into those which match and which don't match. Okay, this is this. Oh, sorry. This approach. Other thing is to not be so sure about the result. Yeah. So yeah, it can be that you say that this document most probably satisfies your information need. This document less probably satisfies your information need. And you can give user a tool which will do what? Which will allow user to start with the documents which you think are more probable to satisfy information need, and define a border by him or herself. So you start with the top documents which with the highest chance, 98% sure, will satisfy information need from our model. So it has all the words which were in the query. And then maybe there are 7 out of 8 words. Maybe there are 5 out of 8 words, but still this is more or less document about the same. It has the major terms which are here. And the user is given a chance to judge themselves about where to stop in retrieving documents. If you satisfy your information need in these 2 documents, perfect. If you need more, perfect. This is the first page of Google. If you need even more, go down and scroll to the second page of Google, and so on. So ranking is the flexible model which first opens the bigger opportunities for returning the result instead of just constraining what matches and what doesn't match the query. We give the scale. We say that more satisfying, less satisfying. And we give user a tool to crawl, to explore these opportunities in some way which this user will prefer. Does he or she want to scroll further? Please do. If you just stick to first page of Google, that's okay. And ranking is a good approach of first loosening the constraints of Boolean retrieval. So it's now allows to grab additional neighbors to this model to bring something which is not exactly matching the query, but which is highly probable matching the query. And also give a user a chance to choose and to show different behavior in this area. Ranking is often preferred. So as I mentioned, sometimes even the query, if it's built in not a perfect manner, it still gives a chance to find the document. So you don't have to spend a lot of time rephrasing the query. I remember the times. Sorry. I remember the times when there was a competition of search. I don't know if it exists now, but it was the competition which Yandex was running in the late 90s and early 2000s, when there was a competition of skilled users of search engine. They needed to build a complex queries to retrieve some specific document. They said, there is a document about something. Please write a complex query which will include and or some wildcards and something, and find the document. This was a competition. Who do it first? Yeah. So today you can just, when last time you did some specific characters in your query, you do some negations, you do some side column and something, just type a query and you retrieve the document. So you don't have to be very skilled in building queries today. Yeah, and this is important when you speak about ranking. The border is controlled by the user. One user needs a single answer to the question. Other user needs to explore the area, this one, and something relevant. When you search for the phone of, I don't know, piano master who will fix your piano, you need a person who will come and fix your piano. You will call the first one in your city. If you want to explore the scientific area in Google Scholar, you type some terms and you will scroll the documents even if they don't exactly match to your query. You need something which is relevant somehow to your question which you explore. And there is a theoretical justification, the principle of probability ranking, which is trying to bring this probability match to ranking. So ranking is based on the idea of probability of returning the correct document. So ranking should be built with respect to probability. So the principle is to rank the documents, put the high probability to what is needed to the top, and lower to what is not that relevant at the point of view of the system. Like again, I repeat the same thing, so we will speed up. Rank candidates by relevance, and the relevance should be somehow matched with the probability. The intuitive understanding of relevance, again, so you remember the document matches and doesn't match your information need. In the Boolean model, it will be ones and zeros in some positions. You can say that if you do, if you consider these as probabilities of meeting, you can do a simple probability formula, which will end up with exactly 1 when all the query parts match all the document parts. So for example, the first one, if you multiply 1 by 1 the query information and retrieval, you will have, like, if you sum up with the scale factor with 2, the query length is 2 divided by 2, you will obtain 1, probability of 1. Yeah. The second document doesn't have word retrieval, the second document, and it will give you a probability of 0.5, for example, yeah, in this Boolean model. You can do ranking using just the simple form of documents. And here, actually, there are two sentences. Information retrieval is helpful for you, for everyone, and information retrieved is helpful for you. So the two phrases, one is more relevant for the query and one is less relevant for the query in terms of just the Boolean understanding of relevance. If you bring here some probabilities, they will be more exact ranking. So not that 1, 0.5, but more shades of scales here. How to do this? You can do this using TF-IDF technique. So I believe you met this in the machine learning course. If not, just an overview. TF-IDF is the way of bringing some weights to words in the index. And you can store these weights also in inverted index. The idea of TF-IDF is to consider both term frequency in the document and together the term frequency in terms of all the documents. So term frequency in the document is what? It can be a simple form, it occurs or not, 1 or 0. It can be a number of documents. This number can be somehow scaled, for example, in a logarithmic way. What does it mean? If you meet a word philosophy 500 times in your document, and you meet the word philosophy 600 times in your document, this means both is a big number. Yeah, and logarithm for these two numbers will be pretty the same. So the importance of word will be comparable. But if you meet word philosophy in this document 2 times, it will be significantly different because logarithm is growing fastly in the beginning and slower in the end. And these are different techniques of how to use number of occurrences of the word in the text to bring the importance. So the bigger number of documents, the bigger number of words in the document, the bigger is the value of this word for this particular document. This is like the term frequency, the weight of term for the document. The inverse document frequency brings the importance of the term itself. It says, I meet the word to in any document. And in this formula, it means what? It's a logarithm of what? N, all the documents, divided by what? All the documents which has this term. So it will be 1 by 1. And when you do logarithm of 1, you get 0. Yeah? The importance of word is what? Is 0. So if the word is met in any document, it's not important. But if the word is met in a very small number of documents, in one document, it will be logarithm of n. It will be a big number. Yeah? And then you multiply it. You multiply the importance of the term itself for the whole collection of documents, for the whole language of Russian, and the importance of this term inside this document. So if the term is very important, so very rare, and you meet it multiple times in the document, that means that the value will be very big. If the term is frequent and you meet it not very frequently in your text, it brings practically nothing here. And this place which is taken by 1 in this table will be 0.00 something, so almost 0. And this can bring you like a better tool for ranking. For home, I suggest you to, if you want some reading, to read the chapter 4, which is about index construction. And now I will try to fastly switch to the next lecture, because this lecture will be exactly connected to this topic. Come on. Yeah. Wildcards and spell checking. Great. So take a breath, 30 seconds. New topic. Okay. Great. So, and now we will speak about the following problem which appears right after you build an index. So now we assume that you understand at least how to build a first simple index for a big collection of text documents. You explode them into terminals, you build an inverted index upon this, and then you use either Boolean retrieval technique or ranking technique to show the results to a user. Yeah, so the simplest search engine you can do. The world is more complicated. Users usually don't approach the good writing in the Russian language. Users sometimes don't know how to write some words, and it cannot be just the case you take a query, you split it into words, and go for a search. You will need to do something else. And what else we will discuss in this lecture. So agenda will be about wildcards and spell checking. Let's go fastly. Wildcards. Why do we need wildcards? So what's actually wildcard? Wildcard is the way of replacing some places of the word by technical symbols, which will allow you to have some variations in spelling. The simplest form is when you're uncertain in spelling of a term. So for example, if you don't know how my surname is written, so you know how it's pronounced, and you're not sure if I'm Protasov or I'm a Pratasov, you will write something like this. Yeah, so we'll place a special character instead of the letter, and you will say either this or this. Place something and find me all the documents which store the surname, which is written like this, with variations in this place. So this is the wildcard. You're uncertain in spelling, like in the case of lasagna from the example. There are multiple ways of spelling the word. I was a student in the school which was teaching me the British version of English. So I'm used to writing words color and neighbor using U. So color and neighbor, yeah. And others who were like in schools and learned the American pronunciation, American spelling, they don't use U here. Yeah, so color, neighbor, OR in the end. So these multiple variants, you aware, and you want all the documents that are relative to this word, but you don't know how other people are using this word. And you use it to apply multiple options. You're unsure about part of speech, which will be the document. So you want to speak about, I don't know, desoxyribonuclease or desoxyribonucleic. Yeah, so you don't know what will be in the end. The whole word you understand, but you don't know what's the flexion. Will it be an adjective or a verb in the end? You don't know, but you want to know everything about this, yeah, about DNA. And the other thing is that the foreign languages, if you know multiple languages, the word university is starting multiple, like the same way in different languages. But in Russian, it will be Universitetskaya, and in English, it will be university. And the beginning is the same, but the flexion. And this oftenly met when we speak about languages which are using the same character set, which are friendly. But for example, you know German. And the spelling of German's name is different in Russian and Belarusian. And like, I can only do what? I can place wildcards in some place of his name to match both spellings. Which are the syntaxes? Are there any standards for wildcards? Actually, maybe yes. The most, how to say it, ancient, because I remember it since 90s, and it was present even before. It's the Joker symbols, the syntax, which includes these two letters as the basis, and some other symbols, maybe like the square brackets, sometimes curly brackets. But the basis for Joker symbols are star and question mark. Star means any sequence of any letters. Question mark means exactly one letter at this place, and you can place them in any position in the string to show that you expect here some replacement, either a random sequence of letters or a particular letter. How to search for such wildcards if you have an index? Yeah, so if previously we were talking about the fact that we know the vocabulary, now you're given like the flexible thing. So how to use your indices to retrieve documents. With trailing wildcards, this is very, I think, easy, with the only change. You remember what was the inverted index? There was a hash table which was storing the words. If you replace the hash table with map based on tree data structure, if you had an algorithms course or something, you should know things like B tree, AVL tree, red and black tree, and so on. They allow you to search for an element not in the constant time, but in logarithmic time, so logarithm from the size of the collection. But they have a very good property. If you find, for example, an element, then the neighboring elements in this tree, they will be alphabetically ordered. So if you go to the right, you will go like decreasing in alphabetic order. If you go to the left, you will be increasing in alphabetic order. So if you want to search everything which starts from Moss, you will do what? You will search for Moss, and you will go left in this search tree. You will go iterate the elements until the substring, the first part will be not Moss, but Mot. Yeah, so the character will change. And this can be done in linear time. That's the good property of search trees. So you use search tree instead of hash table, and then you can iterate through the ranges of values, and this will take no additional complexity to you. So it will be linear in terms of iteration. If you have the leading wildcard, just a simple tree. Build another search tree, which indexes the document from the other side. Instead of city in the end, you will use what? YTIS, which is the reversed word, and search it in this tree. So 2 trees to deal with leading and trailing wildcards, and you're done. You're perfect. You can start doing with this. So how can we handle the word Moss star O? You take 2 trees, you search for candidates, then you merge them by intersection, and you're perfect. You're done. You complete the task. Yeah. So they start with Moss, they finish with O, and everything which is retrieved is matching the wildcard. Harder is here. What if you have 2 wildcards in the middle? This technique will not give you the exact answer. Another syntax for wildcards is very similar, but the symbols themselves are different. These are percent symbols and underscores in SQL. So percent behaves the same way as a star in Docker symbols. So in your SQL queries, you can use like, and like is behaving exactly as wildcard match. So just another set of symbols for expressing the same wildcard. And of course, the extension of all this story is regular expressions. Yeah, so you heard about them, you use them. Regular expressions are the very powerful wildcard tools. So how they do it in databases? Of course, information retrieval, like as I mentioned, is the discipline about searching in unstructured collections of data, where databases is searching in structured collections of data. But it doesn't mean we should use different algorithms in these techniques, in these studies. Of course, we should borrow from each other. And there is the article from one of the creators of PostgreSQL, which says that for now, this is the documentation link, the first link. It says that unfortunately, like operator can give us unexpected performance. And this was an interesting finding for me, that actually in, for example, Postgres, there is no solution for the problem. They still can suffer from wildcards. So if you build a pretty wide wildcard, if you say select star from table something where name like star, what will it do? It will scan through all the table. Yeah, no indexing applied. It will search for all the documents and match them with a wildcard. And also, there are techniques which tries to somehow reuse existing indices. And for example, trailing wildcard here, like call like foo here it is, can use the B3 index, which is a very common index in databases, which do an indexing of strings here, and can use it for filtering out the documents, because B3 is based on alphabetic order of words. So it can run the procedure which I explained in the previous slide. And they actually do this. So if you use the word like vina and star, then it will use B3 and search for words which are starting with vina, and then go to the neighboring nodes and look for those which match with this query. If you look for vin %d, it will find all which starts with vin. So it will consider everything after the wildcard as a trail. So it will find all these documents and then filter them by having d in the end. Yeah. So they consider the smaller amount of elements, but they need to still filter the result. But if we have pretty like the leading wildcard, you will see that they need to consider the very big number of documents, and only one will match. Okay, so still in databases, the technique is pretty simple and not sophisticated. And when you write a query with like, you will suffer from the not perfect indexing. Can we do it better? Can we deal with wildcards in a better way? And the answer is yes, there are multiple techniques. The first technique is per-midterm index. The idea is very interesting. Instead of indexing each word separately, we will try to index it in all possible rotations. So we will add a leading, a trailing special character, but it doesn't matter, trailing or leading, we don't care. So just a marker for the end of the word. And then we will build all possible rotations, okay? So we build all possible rotations. So we will actually do what? We will any position in the world bring to the end, to the beginning. So it's very important to let any letter in the word to stand in the first position at least once. Yeah, this is a very important thing. And then we do what? Having these possible rotations of word, we build a general search tree, B tree, like in the previous slide. And then when we have different wildcards, we can use this extended index for retrieving more complicated cases. For example, if we look for just a string, so there is some sequence of letters, we look for x plus end of word. So we look for such a word which is exactly what we search for, yeah, like x. So we look for x per, dollar. If we use x star, so the trailing wildcard, we say that we know that the word starts here, and we will mark it with a dollar sign, and everything else will be like x star. So we will specifically mark it that we start with a dollar sign. If we use the leading wildcard, so we say what? The word, there's some letters, then it has x, and the word ends. Then we will write it like this. There are some letters which we know, the word ends, and there is some letters which we don't know, we will just move them in the end, because we have this option of rotation in our index. If you have stars from both sides of the letters which we provide, we can do what? We can take these stars and bring them here, because we have all rotations of word. And we will look for what is starting from x and something else in the end. This will bring us exact result. If we have middle wildcard, so we have x, middle, y, it means what? It means that then we expect the end of the word here. Okay? So great. Let's take this part and bring it here, because we have rotations. So it will be y per dollar x star. We will look for this. So we'll try always to bring the wildcard to the end, because we will search for the beginning of the word in the tree index, because we have this opportunity. In tree index, it's easy to search. We will have problems with such thing. Yeah, so there will be a problem in searching for multiple stars. Yeah, so it means that these techniques will not answer this question, and we will need to do what? We will need to sacrifice some part of the word. For example, I don't know, this part. Yeah, so we will sacrifice y. We can search for x star z, and then we will filter out the words which has y in the middle. The example of hello is here. So we have hello. How we will build the query to a per-midterm index. So what we did, we took all the words, we added dollar sign in the end, we built all the rotations, and we prepared the search tree. Now we need to convert the query to retrieve the wildcard. So which of the options this matches? This matches the E case, yeah? So some symbols, star, and the N. So it means that we will search for what? O% hell star. Okay? Yeah, so this will be the query which you will put in the per-midterm index. And knowing this, we will find this match, okay, which was prepared before. O, hell, and L in the end. So this will match. So permuterm index is the first iteration of how to make search for terms more exact when we speak about wildcards. So how to make the pre-select set narrower than rather just any random set of documents. What's wrong with this index? It doesn't handle multiple Joker symbols yet, yeah, so we don't know how to deal with them. And it increases the vocabulary size this number of times. The obvious, what's the average length of the word in your language? So in Russian, it's around 5 symbols. In English, it's around 4.5, maybe in Russian 6. But it means that in average, any word will produce this number of rotations. So the index will be much bigger. So we need more memory, and you still cannot deal with multiple Joker symbols. What can, yeah, a question? Mm-hmm.
So we have multiple like garbage words.
Mm-hmm.
Rotated letters. They have no sense. Why we searching them?
We don't have garbage words. The question is, why do we search for garbage words? Search not for garbage words. We search for representation. The word is stored in the way that we want any symbol of this word to become the first in the index. Because any time you search for the word Moscow, you can forget any of the letters. And if you want to put the star in any position, there should be a way to retrieve the document in the form of X star Y. Yeah. And the algorithm says that for such documents, you need to put the second part in the very beginning. Yeah. That means that there should be representation which will start from any letter of the word. This will allow me to use these kind of wildcards. Because in the previous slide, what we saw, these kind of queries are well served when we have the star in the end, and they are very ineffective when we have a star in the very beginning. If you want to be equally efficient for placing star in any position of the word, we need to prepare the index with some, as you said, meaningless garbage words. This will grow the index, but it will allow us to search with wildcards. So you pay with memory for speed.
This procedure is so fast that allows you looking for example, word or hell. You will never find such one. Yes.
Oh, hell?
Like
But that's why we use this special term. So we always, for any indexed word, we know where is the word beginning and word end. So even this word $hell explains us that actually this is hello. So even the only case which can be that you search for $hell, but why? I don't know. This special character, of course, it's from the permuterm like original implementation. You can use any special character which is impossible to type, for example, in the search query. Okay, let's go forward. How to fight with this situation when there are multiple stars in the middle? One of the approaches is to bring the word down into smaller parts. So how to do this? Starting very similar. We mark the beginning and the end of the word. So we add $signs, but instead of rotating the word, we will split it into 3 grams. 3 grams means 3 letters. And this is how the word castle will be split into 3 grams. And then what we do, we will create an inverted index, not for the whole words, but for these grams. 2 grams, 3 grams, whatever you use here. And this will allow you to do what? To serve these kind of queries. So if you put a placeholder here, you know that there is a sequence of RE, there is a sequence of VE. Yeah, and you will search for such sequences, and you have this bigram index, for example, here. You will go retrieve all the words which have these substrings, and then you will recheck them with this exact wildcard. So again, this will bring you additional non-relevant words, but it's still some filtering. So you can use this technique for some filtering. What's good with such indices? The number of keys is not that big. So if you speak about bigrams, what is bigrams? 27, so all the English letters plus $sign. It's 27 squared. It's nothing. It's like, I don't know, 800. Okay? And that's a technique which can be useful when you want to at least fastly filter some candidates. Of course, 3-gram index will not help you with searching for such a query because it will not, so 3-gram will help, but 4-gram will not help. Yeah, so here we know that there's a beginning of the word, there is the end of the word, but if I add star in the beginning, it will break all the magic, because it can also say that there's definitely VE end of the word, but I cannot provide anything for RE. I can only generate the candidates. I can only attach some random letters and search for them. And it will be a very, again, long procedure. So it will not help me to speed up the algorithm. The second thing is that, unfortunately, not all the kgrams have the same like selectivities, differentiating power. As I mentioned previously, for the words, the same can happen for 3-grams. There will be multiple documents with this 3-gram, and there will be a very small number of documents with this 3-gram, for sure. So how can we deal with this? Here comes a multi-gram index. And this index says that for each of k-grams, first, we will have specific k, meaning that the length of this index part can have different lengths for some particular cases. Some bigram can be very important because it's very selective. So it's very, very cool. So some combination of letters is very rare in the language. And we will definitely store it like these 2 letters separately. But others are more or less useless. And we will need to search for longer combinations of letters. And they will be better in differentiating. And here we introduce the selectivity metric for a gram. We say that some x gram, so k gram, v gram, is very selective when it returns almost every document. So the ratio of documents which it retrieves compared to other documents, it is pretty big. So word the 3-gram the will return all the documents. Yeah, because it's everywhere. The selective power, the selectivity is very high. Yeah. Then we introduce the opposite metric called filter factor. How good this term in filtering. And obviously, term the is not good in filtering. Yeah, that it filters nothing. If you apply this as a filter for documents, it will keep everything the same way. But word Nastya will be very low in selectivity. It returns 3 out of a billion, but the filter factor will be high. It will be 0.9999997. And the idea is to take only such 2 grams, 3 grams, 4 grams with a very high filter factor. That means that whenever you search for such grams, you are sure that the number of documents will significantly reduce compared to the original number of documents. And then when you apply searching for these multiple grams, you order them by filter factor. So you as you do in optimizing the, if you ever heard about relational algebra, no case. There is mathematics behind databases. Just a short comment, which says that we need to run the query, like select something in the fastest possible way. And the idea is to do what? When you apply multiple conditions to search, you want to reduce the amount of initial documents as much as possible at the first stage, and then filter this smaller collection. Or if you want to do a join of two tables, and then you apply where, you select star from A join B. Yeah, you don't want to first join them and then filter. You want to filter them and then join, because it's much less computation expensive. And you want to do what? You first want to take the smallest data as possible and then do operations. Here is the same. Apply the, if you have like the terms in your wildcard, which are very, has a very high filter factor, so the selectivity is very low, then you apply them first. So from a billion of documents, you select 100, and then you apply filter into these documents, instead of doing it vice versa, because it's computationally expensive, efficient. Okay, and then it comes for regular expression support. I will not cover this in details, but what I say that there is a general idea that regular expression can also be converted in some techniques into these 3 grams. So again, just to sum up, first, permuterm index. Let's take the word, transform it in some way, and build the index which considers all the rotations, and it helps us to search for some wildcards. Then someone came. Wildcard is just what? A gluing of parts of the word with these joker symbols. Yeah, so the stars and question marks. What if we consider these parts of words instead of the whole word? Yeah, and this was a perfect idea. 3-gram index, k-gram index, multigram, they all based on the sub parts of word indexed. Yeah, and now we say that we improve the language of queries, but we keep the idea. Idea will be still base your search on 3 grams or v grams, but the language of queries is now more complicated. Instead of just joker symbols, we can use a language of regular expressions. But still, what we do, we search in index. In the end, we go to the index and search for documents. And to do this, we will build what? A Boolean query, like here. And the technique is to do what? Take the regular expression and try to convert it into the best matching Boolean query. This doesn't mean that the query will exactly match regular expression. It can be either exactly the same or wider, and then we will apply regular expression to the candidate list. So first we pre-select the documents which correspond to Boolean query, and then we filter them with regular expression. And the research in this area is just doing what? It's trying to make this projection as good as possible. Yeah, the idea is just to try to build it as accurate as possible. Which are the techniques? So one technique is saying the following. So we can represent our regular expression as a tree, and then we apply some techniques to this tree to simplify it. Yeah. So we have some rules of projecting this into the tree. Then we do some transformations, and each transformation can either keep the tree, keep the meaning of the query the same, or make it slightly wider, so it loosen the constraints a little bit. And anyway, like as you see in the example with William Clinton, there's example from the paper, the final physical access plan. So it's actually, what does it mean? It's a Boolean query. Clint and Nton. Yeah, so here in the end. But the original regular expression was much more sophisticated, and it actually required what? It required William or Bill in this regular expression. Yeah. So the method actually will return the number of documents which is wider than the initial regular expression. but then you can use regular expression to filter out the exact results. This is one of the ancient approaches, like almost 20 years ago. Any other things, like 15 years ago, Google Code Search Project provided another approach. Again, regular expressions, again, trigrams, but they provided the following technique, which, again, so theoretically not exact, but practically it was used in the good Google Code Search Project, which allowed you to search in code. They said that let's provide each, let's say, small part of regular expression with properties. Is it possible to make it empty? So is it just a star means it can be nothing. It can be from 0 symbols up to some number of symbols. Is it exact match? So should the content of this part be exactly matched in the query? Is it a prefix? Is it a suffix? And I don't know, match some other characteristic of does it a match request? And they do what? They recursively union the symbols in this regular expression. So as it in the example. So for example, there is the regular expression saying what? A, then the group of BC repeated some number of times, 1, 2, 3, 4, and so on, and D in the end. So what they say, A is exact match of A, and B, C is exact match of BC group. So there should be BC group in your query. Then D, exact match of D. So they will then iterate. They will say, okay, there are multiple BCs. And what this means that this string should start with BC and should end with BC, okay? And this slightly frees the query. So instead of saying that this should be only BCs in the middle, it can allow, for example, B, C, T, B, C. This satisfies, yeah? It doesn't match with exactly regular expression, but it satisfies the constraint. And then they do what? They attach A and say the prefix now is A, and then they attach D. And now they return back to the original regular expression, and their request will be what? The prefix of the query should be ABC, and the suffix should be BCD. And they retrieve all the documents like this, and then they filter them out with a regular expression. Again, the idea always is the same. We build some Boolean query which is somehow relevant to regular expression, which is either exact or wider, and then we filter results. But this is practically important because it gives us a computational win. Another method, much more recent, again, regular expression is what? Is, as maybe you know from mathematics, can be defined as a finite state automaton. Regular languages parsed by regular expressions, they can be written down in the form of this graph, regular state automaton. And the authors of this paper provided what? They provided the technique of converting this graph into the graph where instead of a single symbol coming, they will do it in trigrams. So how the overlapping trigrams progress you in some graph. And this is like just an expansion of the original graph. So there are some techniques showing how to build one from another, exact match. There are some simplifying procedures, and they then collect the paths in this graph, which will match with the regular expression. So they take the word, they lead it through the graph and say, does it match, doesn't it match the regular expression? Again, the same techniques. So all these things were about that we sometimes use wildcards. In general, when you now use search engines, you do it rarely, you do it not frequently, but still you should know that there are ways of how to speed up the process of searching with wildcards. And I showed you some approaches and even considered some of them in details. Okay, this was about the clever user who actually knows about possibilities. What if the user doesn't know anything about possibilities and just types whatever he or she thinks it should be spelled? Okay, and here comes query correction. Actually, when we speak about spell correction, there are two strategies. First, we need to correct the documents themselves when they indexed. For example, as it mentioned later, if your collection of documents is not, for example, just books edited by an editor, but these are OCR, so optical character recognized documents, as you did in your homework or in your contest, and you saw that, for example, O is sometimes considered as 0. Yeah, the term like the RN can be considered as M and vice versa. Yeah, so there can be errors, and you need to correct such errors to store the document. The second is to correct the queries themselves. Users sometimes make mistaken queries. There are two principles: correct based on proximity. So is this change close in terms of some metric, some mathematical metric like Levenshtein distance, or is it a highly probable change? For example, this is a frequent typo. There are letters C and V on your keyboard, and you sometimes just your finger types V instead of C. This is a frequent typo, which is more frequent than mixing C and P, which are distant on the keyboard. Ways of fixing can be isolated. So you check each word and you correct each word, but it can not catch mistakes which bring a correct word into a correct word, like in case of from and form. And they can be context sensitive. It's more computationally expensive, but you look at the surrounding and you understand that flew from Heathrow to Narita is less probable than flew from Heathrow to Narita. And there are, again, two approaches of how to fix the query. Even if you fix the query, you can do it silently. You can say, I know that you're wrong, but I face it multiple times when I search for non-frequent cases. The spell checker of Google, for example, or Yandex, fixes the correct word. So I'm looking for some non-frequent term, and they say, no, you meant this. No, guys, I meant not this. I meant what exactly I typed. So what you can do, you can suggest a correction. Yeah. So again, being more contact to your user. So instead of just saying you're full, saying you are maybe full, and maybe like you want to change your behavior, but I will do what you ask. So these are all possible strategies that Daniel. So what about document correction? As I mentioned, especially needed when you work with optical recognized documents, correction is important. In some domain-specific knowledge involved in OCR, like letters which are written in a similar form, like O and D, can be misrecognized in OCR, but some letters can be mistyped because this is the typed text. So depending on from where you obtain the source, you can think about typical errors here. For OCR, most probable the letters will be changed on the basis of how they look like. And when you take the text from the Telegram, the letters can be changed on the way how people type. Yeah. For now, we have almost all of us have like the suggestions that maybe this means that the typos are less probable. But if we speak about computer, there is no suggestion right now for correct typing. Yeah. And this is very important. Any document in web, any document, even this is the, you know that there was one of the great storage of information, the Soviet encyclopedia, the biggest encyclopedia in Soviet Russia. It was like 30-something books with all information. It was very well edited, and there are still typos in this encyclopedia. So a lot of people paid a lot of time to edit and fix all the typos, but in any book, almost in any fiction book, you will find typos. That's unfortunately how it happens in the real world. So let's speak about how can we correct an isolated word? So what can we do to fix a typo in a single word? To do this, the fundamental idea is that there is a vocabulary. Okay, there is a vocabulary. You know this vocabulary, and there are correct spellings in this vocabulary. And you can choose what? You can choose a standard lexicon, like the Webster English Dictionary. You can insert a specific vocabulary, or you can build your own corpus of your specific area of engineering, computer science, and so on, because it will also include what? The names, the acronyms, the typical misspellings, and so on. So this vocabulary can be more useful than just a general English language. What else? How can we use the first technique, distance-based, closest-based technique? We can do what? We can compute distances between your query and the possible results in the vocabulary. How to compute distance? Edit distance or Levenshtein distance, and LCS, longest common subsequence. These are two most frequently used techniques of looking for typos. Sometimes they can be weighted. So the distance, for example, Levenshtein distance is based on the changes in the word, and these changes can be with different weight. As I mentioned, for example, if we consider the typing on the laptop, the change of U and I is highly probable. The changing of Q and M is less probable. So I will put different weight to these edits, and then I can do what? I can do ranking of query correction based on the distance. The smaller is the distance, the higher is the chance that this was the origin of the typo. Also, you can use n-gram overlap, technique from the previous part. So you can take n-grams, split the words into n-grams, and measure how many n-grams overlap in these two spellings. Just a slide on edit distance. I will not stop here. Only I will say that this technique is used in Norvik's spell corrector, which you will use in your homework and in your contest. It means that we will count how many operations we will need to do what? To make one word out of another. And these operations include insertion, deletions, replacements, and in cases where it is possible, for example, when I type on the keyboard, it's highly probable, transposition. So I swap two letters this as a single operation. I will put more if I need more operations to change. This is the dynamic programming algorithm, which builds all possible distances for words. Weighted, again, let's stop here. We put weight based on the preliminary knowledge about the model. If it's typing, one weight. If it's OCR, another weight, and so on. What's the problem here? If we speak about distance, if you want to build the number of suggestions to edit your query, we'll need to do what? Still, we need to do all possible matches with all words and vocabulary, meaning you compute the distances from one query word to a billion of vocabulary words. It's very computationally expensive. What can be an alternative? N-gram overlapping is one of the fastest techniques. So instead of doing this, you build index on n-grams, the same one which you used for wildcards, and you split the query into n-grams. You have n-gram index. You go there and you find the words which are sharing the biggest number of n-grams in the query and in the word. So n-gram overlap, fast technique, which doesn't allow you to build any preliminary knowledge about distances between unknown word and other words. How to measure the distance using n-grams? The simplest form is, like, I hope in a machine learning course you had IOU, intersection over union, the metric which shows how many intersect divided by how many are there in both bags. And it's also called Jacquard coefficient. And for example, you put a threshold saying that these typos are possible when the IOU is high, 0.8. And when it's low, we just don't consider such cases. Very good to go. So you build an index, you select candidates based on trigrams, build the list, and then you check them by IOU on passing this threshold or not. An example, how to search for the word Lord. You split it into bigrams. You search for all words which match the first bigram, law, then the second bigram or the third bigram, RD, and then you do what? If you do intersection, you will probably get nothing because this is a typo. Yeah, it's not stored in the dictionary. But then you do what? You apply intersection over union, and for example, here it will be that the word lore has what? It has union equals what? Law or RD from Lord and RE from lore. Yeah, so union will be 4 items, and intersection will be what? LO and OR. Yeah. So it means that intersection over union for the pair Lord and lore will be 2 divided by 4, 1/2. And for example, if I take the word border, the union will be OR and RD 2, but the union intersection will be 2 bigrams, but the union will be 6. BO, OR, RD, DE, ER, and LO. So 6 of them. And that means what? It means that it will be 2 over 6, 1/3. That means what? That the lore having IOU 1 second is highly preferable to border which has 1 over 3. Okay, so I will choose the best match here using IOU for ranking of opportunities. And the question, yeah. You answer me, what should we do? Like here we consider an algorithm. An algorithm says that that's how we rank the typo fixing. Then you say, what if 2 candidates are equally probable? And you're developing the software. So how will you answer this question? I would say that, for example, I would just in one case, I will show a suggest under this word in this search with 2 options, for example. Or I will choose the word which is statistically more frequent in language, because there are, oh my God, there are no words with the same frequency in the language. And if these 2 words, one is more frequent and one is less frequent, I will use a second factor to rank them. So they are equally probable in terms of fixing the typo, but one is more probable in terms of the language. I will use language model for this. Okay. And the last part, what about the case when we want to correct the query, which holds the words which are correct, but they don't build a correct sentence when the context influences the correction. This example I already showed you, the text where the typo is hidden in the correct word. Okay. And we will speak about language models later in this course. It's a very important idea. But how do we search for such typo? So these words are legal, but there is no such phrase in the data set. So we search for it, we get nothing. So we want to do something So we even if we did it, we took the query, we searched for documents, we obtained nothing. There is a question. The words are frequent. The query is not specific. All the words in the query are frequent, but we get no documents. Maybe there is a mistake of a user. How can we work with this mistake? How work with our suggestion? The general procedure is to take a single word and retrieve dictionary terms close to each query term. So we fix the context and we try to fix the typo in the word. So first we fix this context, and then we start fixing the typo in the known word. And we do searches here, and we actually don't succeed. Yeah. Then we do what? We fix this context, and we try to fix the typo here. Okay. And in some case, there will be a match. Yeah. So there will be a big number of documents retrieved, because now we found this mistake. Yeah? And we can then provide this alternative correction to a user, saying that maybe you meant flew from Heathrow, not flew from Heathrow. Other thing is to use by-word statistics. So the language itself is redundant. You know this. I have a lot of slides with different examples. When the missing half of the words in the sentence, you can still reconstruct the meaning of the sentence. In our language, we sometimes use statistically frequent phrases consisting of a lot of words. And you know that, like, if you say President of Russia Vladimir Putin, you can, in the general, omit the last two parts because he's a president for the last 21 years. Then when you can say just a president in the context of this room, you will think about president of this place. Yeah. And this, again, a lot of redundancy in the language. Instead of using 6 words, you can use 1 and you will almost get the same idea. And by-word statistics can be very important here. So how words co-occur together can bring you additional information. You split a phrase into these B words, and then you look into these by words in the search when only one term corrected. And then you enumerate those which are highly probable. So either you work with the whole context and fix one word, or you work with by words. So president of Russia, Russia Vladimir, and so on, and try to fix typo in these pairs. So they are very similar. Just the second one works with just the language model, which can be stored. The bywords are pretty easy to store them in the memory. And what's important, how to count these alternatives, how to estimate the alternatives of corrections in terms of probability. So you need to list the possible changes, you need to rank them, and here you go for 2 things. So first you can do it post factum. So you provide some corrections to users, and users, they do what? They click on this or they don't click. They like this or they dislike this behavior. And this is when you think about query log analysis. So there was a query, you did a fix, user liked it. So this query is highly probable. This fix is highly probable. Or you can rank without considering the behavior of users, based just on the chance that the documents you retrieved with this fix, the number of documents, is bigger than in the original case. Yeah, so you don't care about behavior, you care about probability of having more documents. So this one behavioral, This one just statistical. If you make a typo fix, you just care about that it will give you more results. That's why I usually get this suggestion from Yandex or Google, who say, maybe you meant this, and I meant less frequent term, but they see that this is not a regular query. And how to rank them from this idea. So what we actually do, we want to increase probability of correction, that correct correction. Yeah, so core means correct correction, given the query which is given by the user. And we do what? We argmax means that we check such a correction which will increase the chance that we did it correctly. Yeah, so that this P will grow, and we need this correction. Okay, if you remember the Bayesian law, which is P of A given B equals la 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 la, you will see that this can be converted into this form. So there is also a denominator P of query, but it's constant because this query is given, so you don't have to consider it. The query is given to you, and this is actually how we can utilize language model. So we do what? We want to maximize this product probability of. So actually, probability means what? Probability of either hitting by user the link, or probability of getting more documents depending on your task. So you maximize this so that the corrected query gives you some profit as the company. So it shows more results. It's more highly probable to a user to click it. And second is how probable is actually that this query is a typo in this correction. Yeah. And you just maximize this function. You maximize this and you maximize this together. So how to build such ranking is based on these two numbers. And the last block for the next 6 minutes, because we have 6 minutes more, and the last topic here, what is another technique of dealing with language? So before, we spoke about what? We spoke about lexems, the words, and we spoke about misspellings. Yeah, a long time ago, at the first census, census is when you count people in the перепись населения in Russian. When you count people in the country, and you collect some information about them. What's their job? How old are they? What's their nationality? And this is usually done in every 10 years. So in Russia, we have it this year. And when a person comes to interview someone, like in the United States, like 100 years ago, there were a lot of people who could not write. And I think in Russia also we have such people. You go in the village, there's maybe the person cannot write because it doesn't have arms, or because the person is not attending a school, or did it 100 years ago because it's an old person. And there are people who are coming with a tablet and they write down the answers. And of course, when the person pronounces the surname, it can be a big problem. Then when you don't understand the surname, and how to match these spellings into a single surname, for example. So this is actually the surname is Chebyshev in Russian. It will be written like Chebyshev in English, and it can be even transcribed like this. So it's the same person, but the pronunciation of the surname is like the spelling of the surname will be different. So how can we match these surnames if they're written differently, but they're pronounced and meant to be the same? And here we go to a phonetic equivalence of letters. So previously we were speaking about letters as the smallest part, but the way how we pronounce letters is also very important when we try to fix typos. So this is the origin. How can we use this? Typical algorithm is very simple. We will turn every word into a 4-digit form. And we will do it for all query terms. And then we will build an index for these 4-digit representations. It will give us a lot of false positives, but it will never give us a chance to miss an important thing. How to build such representations? Very simple. We keep the first letter of the word. Then we change all vowels to 0. Then we change similar letters to those which are pronounced similarly and can be misheard by the same number. And then we do what? Remove all pairs when the number repeats. So if you have multiple L's, we will glue them together in a single L. We remove zeros. Zeros means vowels, so we don't care about the O, R, E because they can be misheard, because pronunciation of Scottish person and English person will be completely different in exactly this part, in this 11 or 11 or whatever. So the consonants will be the same, but vowels will change. And then if we have less symbols, if we have, we will pad trailing zeros. So the result is uppercase letter, first digit, digit, digit. So for word Herman, it will work like this. So we keep the last, we keep the first letter, H, and then we convert the letters into numbers. So E will become 0, R will become 5, M will become, R will become 6, M will become 5, A 0, and N also 5, 5. What we do next? We glue symbols together, so it will become H06, 505. Then we remove zeros, H5, 655, and that's all. And these two words will have the same code. So Herman with 2 N in the end, Herman with a single N in the end will be the same name. So if you misheard something, there will be still a chance to retrieve this name from the index. 1 minute left and 2 slides left. Wonderful. Of course, this technique is used to fix typos, but it has very high recall, so it means it doesn't miss anything important, but the precision is very low. And other phonemetric algorithms do exist. So phonetic string matching, which is actually Levenshtein distance plus phoneme representation. Instead of presenting the word as letters, we present it as phonemes, how we pronounce the word, and then we do this match. So another algorithm, which can be, again, all these techniques have some applications in some areas. If we think that our user will pronounce the question instead of typing it, the changes in recognizing pronunciation are more possible than typos here. Yeah, so we will apply these techniques in audio communication channel. We will apply techniques of weighted editorial distance when the person types here. Yeah, and we will do what? We will apply, for example, context-dependent techniques when we speak about typing by a smartphone. Your smartphone disallows you almost to type the incorrect word. So you will type the word, which is from the vocabulary, but it can be a different word. You just made a mistake in this word, and you will replace it with some other correct word. That means that any typo fixing technique will be different for the need of your information tool system. Typing, speaking, or writing by hand, they all will lead to different techniques which you use. So thank you very much. Thanks for your attention. If you have any questions, you're free to ask. If you have any additional questions, you're free to ask them at the lab. I will come today. Nastya, I hope will also come to the lab today. Yeah. Thank you. Thank you. If there are any questions.
Thank you.
Okay, no more questions. See you later then.
Goodbye.